So the last speaker of this session is Arjan Cornelissen from CWI and QSoft, who is talking about near optimal quantum algorithms for multivariate mean estimation.
Yes, thanks a lot, Andras, for the introduction, and also thanks for everyone for showing up here. Because I know it's been a long conference, especially for the Beamer here, and also for us all. So yeah, I'll be talking about recent work that I conducted together with Yassine Hamoudi, who's here, and Sofiene, who's fortunately not here. And this work is on near optimal quantum algorithms for multivariate mean estimation. So let me start by explaining a little bit what the problem is that we are considering in this work. And to that end, let's suppose that we have a probability space and that we have a random variable that is defined on this probability space. And of particular interest to us is that the values of this random variable are d-dimensional vectors with real entries. So this is the setting that we're considering in this work. And of course, we all know that there's particular properties that you can define of this random variable. You can define its mean. I'm sure well, I've seen this. And apart from a mean, there's also something that we call the covariance matrix, which, for the purposes of this talk, we will denote as sigma. And there's one particular thing about this covariance matrix that I want to draw your attention to, which is that on the diagonal of this covariance matrix, we have the variances of the margin of the covariance, right? And especially the diagonal of this covariance matrix will be of interest in the remainder. Now, the problem that we're considering is we want to find an approximation of this mean. And the only thing we're going to consider about our random variable is that we're going to assume that the trace of this covariance matrix, so the sum of the variances of all of these marginals, are bounded or are fine. So we make no further assumptions about our random variable, and this makes whatever we're doing quite generally. More specifically, there's a couple of fields where this multivariate mean estimation problem comes back as a natural problem. For instance, if you're doing physics simulations or if you're doing chemistry simulations. It's also something that's used widely in computer graphics. So specifically if you're doing ray tracing in a lighting. So in some sense, you can see our work as enabling people to play games from one to another. And also, for those of you who were here already for the tutorials, we had the first tutorial by Richard Kuhn on Saturday. And he explained about shadow topology. And when he was explaining this, I was sitting in the audience. I was like, yeah, this can also be phrased as a multivariate mean estimation. So maybe this gives you a little bit of an idea how this fits in the framework of whatever we discussed. All right. So yeah, so we have these two objects, and we want to approximate the mean. And in order to give an algorithm to give an approximation of this mean, we need to know a little bit how we can access these two objects. And so classically, what we can usually do is we can have some procedure that samples from our probability distribution. And then we also assume to have a function that computes our random variable once we have obtained such a sample. Quantumly, we're going to be doing something very similar. We're going to assume that we have some kind of operation that produces a probability distribution with weights proportional to probability distribution in our space. And secondly, we're also going to assume that we have some kind of operation that coherently calculates this random variable. And this ket x of omega here, x of omega is a d-dimensional variable, a d-dimensional vector. So try to think of this ket of x of omega really as like a large binary description of this vector x of omega. So really try to think of it as a tensor product of d-dimensional of d individual quantum states, each of which are a binary string containing the, for instance, a floating point representation. And throughout the remainder of this talk, whenever we call one of these operations, we will refer to this as doing as performing a sample or drawing a sample. So if we are talking about a quantum algorithm that uses n samples, what we mean is that we are doing n calls to these operations. All right. So let me hop into the results that we have obtained in this work. And to be a little bit more precise, what we have done in this work is we have constructed an estimator mu tilde that uses n samples, so n calls to these operations that I just defined. And the probability of the L2 error that we make, so the L2 distance that we obtain from the true, is bounded by some accuracy parameter in high probability. This is the nature of the work we're considering. So with high probability, this setting is satisfied. We have a mutal that falls in this ball radius epsilon n. Now, let's compare a little bit what we can do classically and quantumly and see how that relates to one another. So classically, this question is actually not super interesting because the best thing you can do, has been known for a long time, is that the best thing you can do is just draw n independent samples and just compute the average multiplied by time. And then these are the precision bounds you can obtain. Right? There's no way to obtain an estimate that has a smaller precision. So quantumly, it was known in the univariate case that it is possible to get a quadratic improvement in this parameter n. So here the n is below the square root, here it is not below the square root. But this was only known to be possible whenever the variance of x was known beforehand, or at least the bound of the variance of x was known beforehand. This was like a technical ingredient that you needed in constructing the algorithm. So what we show in this work is that you don't actually need to know a bound on this variance. We show a way of estimating this in the problem. And more importantly, what we also do is we generalize this technique to the multivariate setting, and we characterize exactly what the best precision parameter is that you want to take. So this really here is a theta here. There's no way in which the scaling can be. And the scaling we can draw in a little figure here on the right. And what we can see is that when we plot the attainable precision against the number of samples that we have, then there are two regimes in which qualitatively different things happen. So we have a regime where the number of samples is smaller than the dimension of the vector we are trying to estimate. And in this case, there's nothing better we can do quantumly than classically. So only in the regime where the number of samples we are allowed to use is bigger than the dimension of the vector we are trying to estimate, only there we can get a quantum speed. So this is the crucial observation that we make in this work. If you want to get a quantum speed up, you will need to have a number of samples that's bigger than the dimension of your random variable. All right. Well, since this is a tight characterization, in our paper we will have a lower bound proof and we have an upper bound proof. For the lower bound proof, I'm going to refer the audience to the paper. The only thing I will discuss in the remainder of this talk is how we can get this particular complexity, how we can get an algorithm that attains this precision. So let me explain a little bit what the outline of our algorithm. So just a reminder, we want to estimate this. So the first thing we're going to be doing is we just want to get a rough idea of where this mean is. So we're not going to spend too much work, but we're going to just get a little bit of an idea of where we should be searching. And in order to do this, we're just going to grab a constant number of samples from our random variable and just compute the average. And this is just a very crude estimate of where. Next, what we want to do is once we know roughly where to search, we want to get an idea of how big the spread over a random variable is around this crude estimate that we just found. So more specifically, what we want to do is we want to first find a radius A1 in such a way that if we draw a ball of radius A1 around this crude estimate we just found, and we want that roughly half of the probability distribution is contained in the ball. And after that, we want to find an A2, which is a little bit bigger, in such a way that roughly 3/4 of the probability distribution is contained in the ball with this rate. And we want to iterate this process a couple of times, getting more and more of the probability distributions inside these balls that are getting bigger and bigger. And we want to iterate this process until we have 1 minus 1 over n squared of our probability distribution inside these balls. So more formally, we want to find quantiles AL in such a way, as described here, that the L2 norm of x minus our crude estimate somehow is not sufficient. And so the number of kind of circles that we're going to be finding them in this way, it scales logarithmic in n. So these are all the tildes that you see. color characterizations, they are hiding all these logarithms. And then after, what we want to do after that is we first argue that whatever is happening outside of the outermost ring can never make a significant difference in the mean. So we don't need to care about this. And what we're going to be doing is we're going to be dividing whatever is inside the outermost circle into rings, disjoint rings. And on each of these rings, we're going to estimate the mean individually. So first we start with estimating the mean on R1. So the random variable restricted to only have support on R1. And then we only like to look at R2 and etc. So this is going to be the general outline. Okay. Then there's two things that we still need to consider. First, we need to consider how we are actually going to estimate these quantiles. And second, we need to consider how we are actually going to estimate these expectation values. So first, how do we estimate these quantiles? Yeah, so just a reminder, this is what we want to do. We define y as like the L2 norm, or the difference between a random variable and the crude estimate. So let's suppose that this is the probability distribution of y. Y is now a univariate, a random variable. Now what we can do to start off is to grab just a constant number of samples from our random variable y, and then just find the median of all of our samples. And this median will roughly be at halfway through the probability distribution. Now what we can do is we can kind of renormalize the right-hand side of a random variable here. So define a new random variable y, which is restricted to the case where y is bigger or equal than the quantile we already found. And now we can sample from this random variable again and do the same thing. So again, sample a constant number of samples, and then taking the median of that one. And then it's not so hard to see that this thing will roughly contain 3/4 of y on its left. And we can continue this process, obtain an A3, and then etc. until we have all of these logarithmic number of quantiles we want to have. Now, if we count how difficult it is to do this, the only difficult thing to do here is to sample from these restricted distributions. And more specifically, in the 11th step, we know that the random variable we are sampling from has weight or has probability around 1/2 the L minus 1. So if we want to amplify this event of happening, then we need to spend we need to spend square root of the L minus 1 number of iterations with amplitude amplification. And it is this square root that really here's the quantum that's coming into the output. And so we can see that in our final step, in order to get an event that has probability roughly 1/n squared, we need roughly n calls. So this comes back to what we set out to do, estimate an estimator that makes roughly n calls. All right, so this whole procedure makes around about n calls. And in this way, we can find all of these quantiles and subdivide our domain in all of these rings. So now all that we need to do is we need to figure out how we can actually estimate these means on all of these rings individually. So to that end, suppose that we take this ring, RL, and we want to know how we can estimate this expectation value of this random variable restricted to being on this ring. Now, what we know is that the probability of being in this ring is approximately 1/2 to the L. Reason being, probability outside the probability of being outside the outer radius was roughly 1/2 to the L, and the probability of being outside the inner radius was 1/2 to the L minus 1. So different 1/2 to the L. And so, as a first step, what we can do is we can amplify the probability of being on this ring. And this again takes us about square root of the L number of columns. Next, what we're going to be doing is we're going to define a grid. So this you have to kind of envision as being a dual grid. And all of these points in this grid are vectors also in d dimensions, and these vectors we denote by u. And the side length of this grid, we're going to be let it scale inverse proportionally to the outer radius of this ring. So the bigger the rings are that we are considering, the smaller the grid that we're going to be defining. And what that means, what the benefit of this inverse scaling of the side length is that if we take the inner product of any point in this grid with any sample that we take from this grid, then the absolute value of this inner product will most likely be bounded by 1. So for the vast majority of points in this grid, if we take the inner product with the sample from this grid, the inner product will be bounded by 1. And the benefit of this thing being bounded by 1 is that we can manipulate this as an amplitude in the quantum state. So we can build quantum states where the amplitude of our quantum state is actually this inner product. And this allows us to do computations with this inner product. So this is why it's crucial that we have this grid scale down whenever we have the ring scale up. Otherwise, we cannot encode it as an amplitude. Now, with these techniques, which are called oracle conversion techniques, we can do the following thing. And here I'm hiding some details that I will have to refer to in the paper. But with these analog conversion techniques, what we can do is we can build this operation, which in the phase calculates the inner product between vectors u that come from this grid and the expectation vector that we want to estimate. So this operation in the paper we call a directional mean oracle. And we can see that whatever we want to know is somehow encoded in the phase of this operation. And now what we can do is we can define this function f of u, which kind of takes this points in this grid and take inner product with this vector that we want to know. And we can see that what this operation is doing is it's actually computing this function f in the phase. And because it's doing that, we can run something called gradient estimation. We are in the setting where we can use the gradient estimation algorithm to actually find the gradient of the function. And this gradient is exactly the vector that we want. So this is the next step in our algorithm. We kind of use this directional means oracle as a subroutine in the gradient estimation routine, which allows us to get an L-infinity estimate of this vector that we're on. And if you then do the analysis carefully, what you'll find is that the precision that you obtain scales roughly like this, the square root of the trace of the covariance matrix over the number of samples taken. But the gradient estimation routine will give you an L-infinity estimate. But in our results that I mentioned earlier, we wanted to have an L2 approximation. So in order to get that, we have to convert using Hilbert's inequality. And this gives us the extra square root of the that was present with the scale that I mentioned earlier. So now we can, sit back a little bit and think about how all of these steps fit together. And one thing that I think is important to notice is the reason why it is nice to kind of like divide your space up in all of this. Because if we look at the inner mode ring, so where L is small, we can see that the number of calls that we spend in the amplification phase of the routine are very small. We are not amplifying too much. We're not doing so much work in the amplification stage of the algorithm. Rather, we're spending a lot of work in the gradient estimation part of the algorithm. And this is because a large part of the probability distribution is located in these inner rings. And therefore, we need to know very accurately what is expectation value of our random variable restricted on the inner rings. But then when we're going further out to the outermost ring, we're spending more and more work in amplifying first what's happening in the outer rings. And then we can get away with a little bit less precision in our gradient estimation. So this kind of signifies a little bit why it is nice to kind of like divide up your space in these different regimes. All right. So this brings me to the concluding remarks. So this is the main result of that we arrive at in this paper. we provide a tight characterization of the precision we can obtain in a multivariate mean estimation algorithm. And then there's a couple of open questions left. One thing we can kind of ask ourselves is what happens if we don't demand that we have a probability of a third of having a failure, but what if we want to change this to be like probability delta? Then in the classical world, there's a lot of work on trying to kind of like get precise dependencies in these regimes as well. And we can see that there's actually some weird scalings where somehow this logarithmic factor, depending on delta, does not come back in one of the terms of our precision. So it will be interesting to see if in the quantum world we can get something similar, or at least try to figure out how these two are related to one another. And in the classical world, it is even known, or people are working on, what the constant factors are in the big O notation. So obviously in the quantum world, we also try to get a handle on that. It's also interesting to see if we can do something about this L2 norm. Can we also find an optimal estimator in the L infinity norm, for instance? This is something that at this point we don't know, and would be nice to figure out. Then a third thing that we can adapt is we can adapt the access model. So this is the access model that we consider, having a binary description of a vector access omega. But you can also consider maybe that this random variable is not given to you in terms of a binary vector, but more in some kind of analog setting. And if that's the case, one can, for instance, consider the input being given like this. And in our paper, we do a lot of work to also consider like this specific setting, and then try to also find optimal error dependence in this regime. And then the final question that we have is, suppose that we know a little bit more about this, about sigma, about this covariance matrix. If we have a little bit more idea of its structure, can we also know a little bit better how we can build a quantum algorithm? Can we somehow exploit it in order to get a better algorithm? So these are the open questions. Thank you.
Thanks for the nice talk. I think you said towards the beginning of the talk that the first bound, the one over n, was known if you put a constraint on n. So what is that constraint? What is that bound?
Shall I go back?
Oh, did you write it down? I didn't see.
That's here, you mean, right? Yeah, so if it is known beforehand what the variance of x is, or if you have a known upper bound on the variance of x, then it was already known.
I see. So just any upper bound.
And well, you would have to replace this variance of x
with the upper bound. Okay, I see. Okay, cool. Thanks.
So you sort of split up the input oracle into something, some probabilistic oracle, some oracle for the probability distribution, and then some function to compute all of these values. Do you think this will also still work if you get something that immediately just gives you a big superposition over all of the XWs and not gives you a superposition of the Ws first?
Yes. So our algorithm kind of always takes first a call to like this distribution oracle, and then a call to the random variable computation. So you can merge this into one element. But for instance, if you go to the setting that I mentioned in this open problems part, where I'm going here, like what's interesting is that if you consider a setting like this, then not even the number of calls that you need to make to the one oracle matches the number of calls that you make to the other. So you get like two different query complexities that might be different from one another, but still simultaneously optimal.
So in your problem, you consider this L2 norm error on the mean. Can you motivate an example where that comes up? Because like one of the examples, for example, shadow tomography, there we just think of there being d separate random variables, and you just want to get each of them, like they have nothing to do with each other. You just want to get them all to additive error epsilon. So that would be like infinity norm. I'm trying to imagine where does this 2 norm picture come?
Yeah, that's a good question. So our main motivation for considering the L2 norm is because most of the classical literature also considers L2 norm, and in the classical case, this is somehow the most natural thing you obtain. So if you do the analysis of why it is Monte Carlo sampling in the classical case, attains this error bound, then the L2 norm comes up most naturally. So in order to be able to compare like nicely with the classical literature, we decided to phrase everything in the L2 norm. Okay. But our techniques you can quite easily adapt to also get estimates in different norms. For instance, as I mentioned here, like in the gradient estimation step, you already directly get an LNPS norm. So you can convert this into any other norm, any other LP norm. Quite easy.
Thanks. Thank you for the talk. So if I understand correctly, classically, the variance is pretty much the only moment of the distribution that's useful in bounding the number of samples that you need to estimate the mean, like bounds on the kurtosis or the skewness or whatever. I don't know if those are useful, but I think no. Is the situation at all different quantum mechanically? Like if I give you an a priori bound on your favorite higher order moment, can you use that at all?
That's a good question. So we didn't consider this question. I would be surprised if you could, but I don't have any legitimate argument to back that. I suppose. Maybe if you know somehow that the skewedness is big, then you kind of know that there must be something like pushed towards the outside of the distribution, right? So maybe you can then get away with already knowing beforehand a little bit how big your radii would have to be. Maybe there's something to exploit, but I would be surprised if it would give you really something like meaningfully.
I see. Okay, thank you. It's a very open-ended question, I guess.
Sure.
Yeah, it seems to me that you can exponentially suppress the failure probability by simply getting like multiple independent estimators and taking the median. So is this idea correct?
So if what you care about is an infinity norm estimate, then yes. But if you want L2 estimate, then I think there is counterexamples that you can find for just reducing the error probability by like in this way. So I think you have to do something slightly more elaborate, but like in the end, the technique that you need to use is well, yeah, it's not so much more involved than only taking.
Okay, thank you.
Just for comparison with the classical results, if you wanted to indeed just have an L infinity, so like a coordinate-wise estimate, are there classical bounds in that scenario?
Yes, I think there's not so much more you can do. I'm also looking at Yassine for a little, but I don't think there's so much more you can do than what is mentioned here. Even if you're interested in an L infinity norm estimate, then yeah, as far as I know, this is the best thing.
So you kind of get the same complexity usually as for L2.
Yeah.
Yeah. Right.
Thank you very much. Nice, clean result. Could you comment a little bit about your oracle assumptions with regard to the data loading problem, in the sense that this can't apply to arbitrary distributions. We have to have distributions that have this oracle access. Can you just comment on like how can it be overcome?
So in that sense, let me. Yes. So kind of whatever assumptions we make in the quantum access model kind of mimic whatever assumptions we make in the classical access, right? In a sense, I always view whatever we assume here to be roughly equivalent to what we're doing here. So in that sense, yeah, I think they're roughly equivalent. Does that answer your question? Quantization. Well, so if you can somehow implement the procedure here, then usually you can also quite easily like make that quantum. I don't know if there's some kind of easy way to kind of do the reverse. Perhaps. I guess it depends really on the application you want to use. So, yeah, maybe that's more application dependent.
Yeah, sort of related to that question, would your algorithms work if in the distribution oracle, you had like attached to the cat W, like an arbitrary junk state psi W.
Yeah, because you can take this extra junk to just absorb. Yeah, you can absorb it in the definition of omega. So
okay, yeah, I think that can be instantiated in quite a few different situations. I think like if you allow for junk, and which, yeah, I think that can be instantiated in quite a few situations.
I see. Yeah.
Yeah.
There's also one online question. James Cruz is asking, can we say something about the case where we have heavy tails? So the strong law applies, but not the central limit theorem.
That's a good question. This is not something we researched. So I guess I will have to say that it would be nice to look at. I guess I can say that it would be nice to look at, but we haven't looked at it. So
Thanks.
Yeah.
Right, let's thank Arjan and all the speakers of this session again.